So now we're going to discuss how some of the problems caused by hazards in the pipeline can be solved. So let's go back and look at the example again, cycle 3 of the very first example, where we do have read after write dependence. So this is a write, in that we write a new value into register A, and this is a read, in that we use that value, we read the value from register A. And as we already noticed, that we will actually not be able to get the new value loaded into register A by this instruction already in the next cycle because of the fact that we write the new value into the register file first in the write stage of the pipeline. So what can we do to solve this? Well, we could turn to static solutions. So we could say to the compiler, Mr. Compiler, since you're so smart, can't you find all the cases where we have read after write hazards? And of course, the compiler can easily find these where you read a register value that was written just before it. And please, Mr. Compiler, just put in a no-op operation, an instruction that does nothing in between these two, and then the world will be a much better place to live. And of course, we have to put in the stall up here to solve this problem as well. That's one way to do it. You can also come up with a dynamic solution. So you can ask the hardware designer, since you're so smart hardware designer, why can't you design some hardware that can detect that the previous instruction its goal in life is to update the register, and the following instruction wants to read that register. Why don't you simply stall the pipeline, automatically make sure that no instructions are inserted in the very next cycle? And that's just two different ways of creating a bubble in the pipeline. So they work equally well. But a much better static solution is to tell the compiler, hey compiler, since you're so smart, can't you try to reschedule the instructions in a way that these kind of data dependence, read after write dependence goes away? And compiler can readily do this. It's not that hard for a compiler to do this analysis. It will see that all these instructions are in the same basic block, which means there is no branches here. They are always going to be executed one after the other. And that means that it's completely safe for the compiler to change the order of some of these instructions under certain conditions. And if you just change the order between B and C, the programmer will never be able to tell the difference because it's not visible to the program. It's still application will still perform the right operation. But now we pulled the dependent instructions further apart from each other. So assuming the early write semantics in the register file, we will actually be able to solve this problem. So this is another static solution, so a compiler solution. Another way to solve this, a dynamic solution, is to go back to the hardware people and say, can't you throw a little more hardware at solving this problem? So at the end of the execution stage, that's when a value it comes out of the ALU. Can't you create a shortcut here so that if we know that the very next instruction is interested in the output, the result of the previous instruction, we could create this shortcut or forwarding. So it's something called bypassing or forwarding to the execution stage, so it sort of can eat its own output in the very next cycle. And we need to do that since it's a five-stage pipeline. We need to have a kind of bypass right after the memory read stage as well. So if we create these two bypass and we make sure that we control which input data the execution ALU uses, either the normal path or one of the two bypassing paths, then we can actually make this whole problem go away. So the way this would look in our schematics over this pipeline would be to introduce these red lines here. So I have a red line that feeds this mux. You remember this mux sitting here, choosing between the two green in arrows. So now this mux, the bits controlling we have to have at least 2 bits of control. So we can choose 1 out of 4 inputs. So if the hardware has detected that we have this kind of hazard going on, then it will choose one of these two bypass paths to feed the ALU instead of the normal green arrows. Likewise, we have another bypass path, two of them going to the upper max. So this would be, both these maxes would now be four-way maxes. And these could either be controlled, typically it would be controlled by some piece of hardware that would detect that something went wrong. But you can also imagine that you could give this responsibility to a compiler as well. So the compiler would have to detect data when there is this kind of read left to right hazard. And when it did so, it would create some special magic instruction that says, by the way, this is an instruction that's involved in the read left to right hazard, and control the maxes. But typically, hardware in such a solution will detect this and take away those data hazard problems. The other problem we're going to discuss here is the branch delay problem. So you remember the branch delay is the fact that we don't know the outcome of the branch until the Brown instruction is in the last pipeline stage. That means that we will have to wait, insert three bubbles in the pipeline. Either we ask the compiler to do this, to insert no ops, or we have hardware detecting that it's a branch, and therefore it will automatically insert two of these stall cycles in here until we know it's safe. We know the outcome of the branch, so we know whether we're going to go back to A, or we are going to go to the very next instruction that I assume would be called the E instruction. So that's the problem. And of course this adds extra cycles. So we execute these 4 instructions, and it's actually going to take us 8 cycles per iteration to execute 4 instructions, because we have to add these extra stall cycles. If we have a long basic block here, so if the number of instructions with no branches in it is long, so if we have 16 instructions and then a branch, maybe it's no big deal. But if we have basic blocks that are just 4 instructions long, then this would sort of cut our performance in half. And unfortunately, the basic blocks aren't that long. So 4, 5, 6 instruction basic blocks are quite common. So we have to solve this somehow. So one way to do that would be to do a more aggressive design. So we're going to design this with hardware. The problem in hardware, once more, is that we need the outcome of the branch has to be known at the instruction fetch early on, so we can fetch the very next instruction, be it A or be it E. The right instruction has to be fetched right after the branch instruction has moved on. But we don't know the outcome of the branch until much later. So what you can do here would be to duplicate some ALU. Instead of having ALU do all this double working on both branches and loads and stores and ALU instructions, we could dedicate some hardware and move them early on in the pipeline stage. So here's the problem, right? That takes until very late in the pipeline until we know the outcome of the branch, as well as know the next the address that we're going to jump to. We take the PC value. This max here chooses the PC value, and some immediate here, and we're going to add the immediate and the PC value together, and that will produce the next address. And then we're going to, depending on the outcome of the branch, whatever bit is stored here, we're going to choose either the yellow path or the purple path, which is the yellow path is the branch taken and the purple path is branch not taken. So the fix here is we're going to duplicate, instead of having this ALU do that kind of work, we can actually move lots of stuff earlier. So if all we're going to do is take this immediate and add that to the next PC value. And that, of course, we can do early on. We don't really need to read in the register outcome to do that addition. And then we have to have an extra box not shown here that just tests to see if a register is equal to 0 or not, and then controlling this max. So that removes some of the problem. Another trick, so that was the dynamic trick where we had the hardware solve the problem. Another solution would be static trick. So static trick would be to have, have the compiler solve the problem, at least most of the case solve the problem. So what we could do, for example, is to just by convention, we say, we can ask the compiler, could you produce two different kinds of branches? You can do produce a branch that predict that it's taken. Okay, so what you would do in that case would be that we would execute the successor instruction, and if it turns out that this was the wrong guess, the branch we predicted was taken, but it turned out it was wrong guess, we somehow have to be able to squash that instruction in the pipeline before it performs any harm. So this may work very well. This squashing business could be somewhat complicated, but we're going to do much more scary things than this down the road. This would work very well. The only problem is that it's very rare that branches are not taken. It's much more common that branches are taken, actually, especially if you think about the tight loop that may be common in execution. So this would not cover more than maybe 30% or so of the conditional branches. So it would be much better to predict that the branch is taken because it's much more common. So let's predict that it's taken and start to execute instructions on the branch path. Only problem is that well, you have to have the squashing business, but the other problem is you don't know where to branch to. You have to calculate. You have to make that ALU operation, adding this immediate and the PC before where to branch. So it still doesn't really solve the problem. So one of the nifty ideas that came out of the RISC project at Berkeley, and this actually had been proposed before as well, but it was marketed really well by the Berkeley people, was to implement what's called a delayed branch. So what this says is that by convention, let's decide that the next couple, next instruction, couple of instructions, 3 instructions, whatever it's required by the architecture, let's define that those instructions are always executed. Okay, so you execute some number of instructions. So let's say you did this branch hazard adds 1 useless cycle, 1 bubble in the pipeline. Let's by convention decide that that bubble in the pipeline is not a bubble. It's always going to be executed. And ask the compiler to do its best to fill that slot with an instruction that would have been executed anyhow. And if it cannot find any instruction to put in that slot, it puts a no-op operation that will do no harm. So the first time I saw this idea, I thought it was a brilliant idea, because now we completely solved the branch hazard, the control hazard problem. But the drawback of this is that this is a visible, software visible fix. Okay, so this is if we decide that an architecture today needs the control hazard of an architecture designed today needs 1 bubble in the pipeline, that means that compiler should find exactly 1 instruction and put there. But what if the technology changes, so I need 2 bubbles in the pipeline in 10 years and 0 pipelines in the pipeline in 20 years? Well, now I have designed an instruction set architecture, which is actually very dependent on the implementation and the technology. So it's not nice to solve these kind of problems by exposing them into the instruction set architecture. It's not for backwards compatibility to force compilers to take this kind of stance and to make a hard decision whether there should be 1, 2, or 3 bubbles in the pipeline. Anyhow, this was suggested and actually has been implemented in commercial processors. So the Spark processor, for example, does have this what's called the delayed branches. And the way the compiler will go about trying to find instructions that are safe to put in this bubble place, which is called the delay slot of the delayed branches. There are a couple of tricks to do that. Either, let's say you have the branch right here, So this is the original code. And this branch here has no data dependence on the previous instruction. It's not, if it was an if r equals if r1 equals 0, then there would be a data dependence between these two, read after write dependence. But since there is no dependence between these two instructions, it's actually safe to, in the optimized code, take this addition and put it in the delay slot. So this slot here, the gray slot, would always be executed after the branch. And if the branch is taken, that means we're going to take this path down, we're going to execute the instruction down here, and if it's not taken, we're going to keep executing the very next instruction here. So that's safe to do. You can also put if in this case here, there is a data dependence between the previous instruction executed just before the branch, but then you can look at the instruction in the target of the branch. So the branch would jump to this instruction. And if you can convince yourself that it's safe to do so, you may move this target instruction into the delay slot. So now, when you execute, use this instruction, followed by this instruction, it takes one cycle before you know whether the branch is going to be taken or not. You execute this instruction, and then you jump up here, and now you already did the work you're supposed to do with that instruction, and you can instead do the next instruction in sequence up here. Or what you can take something from the fall through path. So if the you have the branch here, and if the branch is taken, we're going to jump it down here. But if it's not taken, then we're going to continue to execute the subtract instruction here. What you could do, if you can determine it's safe to do so once more, would be to move the fall through case into the delay slot. So if the fall through is a common outcome, then you will actually already have done this instruction before you know the outcome of the branch, and you can go off and do some better things down here. So that is once more a static technique, and as I said, it's commonly used in Spark processors, and it's not regarded as a very clean solution.